Okay, welcome everybody to the final session of the types and control structures part of FSCD. The next talk will be given by Francesco Gavazzo. The title is Resource Transition Systems and Full Abstraction for Linear Higher Order Effectful Programs, joint work with Hugo Dalago. And it will be a recorded talk, and Alejandro will start the recording now.
Hello and welcome. In this video, I will present our paper, Resource Transition Systems and Full Abstractions for Linear Higher Order Effectful Languages. My name is Francesco Gavazzo, and this is a joint work with Hugo Dalago. As suggested by the title, the main topic of our paper is program equivalence, namely the study of notions of equality between programs. And we are actually interested in program equivalence for a specific class of languages, namely higher order languages, that is, languages in which programs can be passed as input to programs, as well as returned as output by programs, so that we treat program as data. Moreover, we want languages to have primitives to perform computational effects, such as operations for printing strings, raising exceptions, or even sampling from distributions. And finally, we are interested in languages which are resource sensitive. And by that, I mean that not only programs are data, but also that data are resources, which means that we are not allowed to copy and erase data unless explicitly authorized. And with a little more precise, we are interested in languages that do that by means of linear types. So at this point, the question is why? Why program equivalence, and why program equivalence for higher order languages with computational effects and linear types? So let me try to answer this question. And let us begin answering the question, why program equivalence? A broad, and I would say historically grounded answer is that program equivalence is a fundamental tool to perform extensional reasoning about programs, which is crucial in fields such as program correctness, optimizations, and refactoring. Just to see a concrete example of that, let us consider the program in the left part of the slide, which performs the addition between two optional integers. Now, we may want to factorize that program using an explicit monadic style, this way obtaining the program in the right part of the slide. What we would like to say then is that these two programs are extensionally equivalent, meaning that if we treat them as black boxes, then we are not able to tell them apart. Starting from the 60s, several notions of program equivalence have been introduced for pure higher order languages, such as contextual equivalence, logical relations, applicative bisimilarity, and denotationally based equivalences. And all these equivalences share some crucial properties that make them a successful tool for program analysis. In particular, they are indeed equivalences, so that one can apply ordinary equational reasoning on programs, and most importantly, they are congruencies, meaning that we can reason about program compositionally. That holds, however, for pure languages only. And that is a strong limitation, as real-world languages are deeply effectful. They can raise exceptions, perform output operations, and also exhibiting probabilistic behaviors, as in probabilistic programming. And that, of course, in combinations with higher-order features. For instance, we do not need to call into play advanced and sophisticated programming languages to see examples of all these features at once. In fact, the code in the slide is a higher-order Python program which raises an exception, prints a string, and samples from a distribution. For that reason, in the last decades, there has been quite a lot of work to extend the theory of program equivalence from pure to effectful languages, which led to the extensions of all previously mentioned notions of equivalence to several classes of computational effects. So far so good. Up to this point, everything works fine and there is nothing new under the sun. However, things get more complicated when one realizes that sometimes focusing on the extensional behavior of programs is a too strong assumption, exactly as it is, borrowing a phrase from Simone Martini, assuming the friction to be negligible in physics. In fact, there is a growing interest in understanding not only the extensional, but also the intensional behavior of programs, meaning that instead of treating programs as black boxes, one is interested in observing some internal features of programs, such as resource consumptions, information flow, program sensitivity, or quantum data manipulation. A well-known and successful technique to deal with all these features is to endow programming languages with linear type systems, so that now data must be used exactly once in programs unless they are under the scope of the so-called exponential modality, which makes a piece of data freely available. Again, we do not need to go far away to find examples of languages having such type systems. For instance, linear types, as well as some of their variations, such as graded type systems, are used in programming languages such as Rust, Linear Haskell, Granule, as well as in quantum programming languages. And notice also that all these languages integrate linear types with higher features and computational effects. For instance, quantum programming languages crucially combines linearity and probabilistic behaviors. That directly led us to the core questions of our work. How do we define program equivalence for these languages? That is an interesting question because the interaction between linearity, effects, and higher-order functions breaks some standard equation one has in the extensional theory of higher-order languages with effects. As an example of that, let us consider the case of distributivity of lambda over probabilistic choice. This equation is unsound in the probabilistic call-by-value lambda calculus. And to see why, let us just think about using the terms in the equations in a program that evaluates its input and then copies it twice. Now, if we plug in the context the first program, then what we see is that we just copy the whole program twice, and then we pass it an input. This way we're solving the probabilistic choice. So what we do is to first copy and then duplicate the program. And only after that, we evaluate each of these copies. This way we're solving the probabilistic non-determinism twice. On the contrary, if we plug in the second term, then we first evaluate it. This way we're solving the probabilistic non-determinism. And once such a non-determinism has been solved, we copy and actually duplicate the result. That is, we first evaluate the program and then copy the result. So the key point here is that we can either first evaluate and then copy, or first copy and then evaluate. And if we have probabilistic non-determinism, these two strategies produce different results. But what happens if we cannot copy programs anymore? Well, in that case, the equation becomes sound, meaning that in a linear setting, lambdas indeed distribute over choice. What is unsound is the distributivity equations of the bank modality. So it is natural to ask whether we can find a good notion of program equivalence that validates distributivity of lambdas but invalidates distributivity of the bank modality. And what it turns out is that finding such an equivalence is non-trivial. For instance, one can of course rely on contextual equivalence for that, and that works fine, except for the fact that contextual equivalence is often practically not usable. And other equivalences available, such as logical relations, applicative bisimilarity, and trace equivalence, either have the same complexity of contextual equivalence, or they do not meet our condition. For instance, trace equivalence validates distributivity of lambda, but also distributivity of the bank modality, and thus it is unsound. And here comes the main contribution of our paper, namely the definition of a resource-sensitive notions of program equivalence for a call-by-value lambda calculus with linear types and arbitrary algebraic effects. Our notion of equivalence works by comparing tuples of programs rather than single programs, with the rationale that programs in the tuples represent the available, either linear or duplicable, resources that the environment can use. To define such an equivalence, we endow our calculus with a resource-sensitive interactive semantics, given in the form of allowable transition systems, and define program equivalence as trace equivalence for such a system. The main result that we show is that such a form of trace equivalence, which actually resembles an environmental bisimulation, coincides with contextual equivalence, and thus it is fully abstract. To the best of our knowledge, this is the first co-inductively based, fully abstract equivalence for calculi with algebraic effects and for recursion, even without linear types. In the remaining part of this talk, I will try to outline our contribution in a more precise way and in a slightly more technical form. So let me begin by recalling the target calculus of our work. That is just a linear lambda calculus with algebraic operations in the spirit of Plotkin and Power. We rely on such operations to produce computational effects, example of those operations being probabilistic choices, output operations, or operations for reading and writing a global store. To model linearity constraints, we endow the calculus with a linear type system with exponential and recursive types, as it is customary in linear calculi. Finally, we give to our calculus an operational semantics relying on a monad T modeling the effects produced by operations. So for instance, we use the distribution monad to model probabilistic calculi and the global state monad to model imperative calculi. Using the monad T, we endow the calculus with a call-by-value resource-agnostic monadic evaluation semantics, meaning that the result of evaluating a program is a monadic value, such as a distribution of values in the probabilistic case or a set of values in the non-deterministic case. The semantics is rather straightforward, and the only things to observe are that we use monadic binding to evaluate sequencing, and that we interpret operations in the calculus as algebraic operations on the monad. So that, for instance, we interpret probabilistic choice as weighted convex sums between distributions. All of that is actually pretty standard in the literature on languages with algebraic effects. So let us now move to the main question of this talk. How do we equate programs in our calculus? Of course, we can define a suitable notion of contextual equivalence relying on an observation function that tells us what is the observable outcome of the executions of a program. For instance, in the probabilistic case, we may observe the probability of convergence of a program, whereas in the purely non-deterministic case, we may observe either may or must convergence of a program, and so on and so forth. That works perfectly fine, except for the fact that such an equivalence is practically not usable. Moreover, as already said, other standard notions of equivalence, such as applicative bisimilarity, logical relation, or trace equivalence, do not meet our desiderata, as they either invalidate the distributivity of lambda or they validate the distributivity of bank modalities. To overcome this issue, we give an interactive and resource-sensitive semantics to programs that highlights how programs are produced and how they can be consumed when interacting with an external environment. Let us see an example of how such a semantics works. We begin with a program E that we have to evaluate. Now, instead of working with just the program E, we work with the program together with an environment in which we collect all the values produced during the computation. And we actually split the environment in two parts. The first one storing the exponential and hence duplicable programs, and the second one storing linear values. Now, what we can do with programs, and actually with programs in environment, are basically three things. We can evaluate programs, we can duplicate duplicable terms, we can pass inputs built using the available resources in the environment to functions. Okay, so suppose we start with the program E and the empty environment. The only thing we can do then is to evaluate E, say producing an exponential value, bang f. Now, as we have produced such a value, we put it into the environment. And because the value is exponential, we actually put it into the exponential environment. At this point, again, there is only one thing that we can do, namely to duplicate f and to evaluate it. Notice that because f is duplicable, we actually leave a copy of it in the exponential environment. Now we evaluate f, producing a new value, say lambda x.g, which we now put into the linear environment. At this point, there are two things that we can do. One is to re-evaluate f, so that we will have a new linear value, lambda x.g, into the linear environment. And that's two copies of lambda x.g into that environment. The other option is to pass an input to one of the copies of lambda x.g. And actually here we mimic environmental bisimulation. And we use terms in the environment to build the input to pass to lambda x.g. However, now all the values that we use to build such an input coming from the linear environment will be consumed, and thus we will erase them from the environment, whereas we leave unchanged exponential values. So summing up, the states of our transition system are tuples of terms made of an exponential environment, a linear environment, and possibly a program to evaluate. We have four kinds of actions. The first one is to evaluate a program. Notice that here the program may actually produce some effects, namely actually those prescribed by the monad T, meaning that our transition systems will be a monadic one, such as a probabilistic transition system. The second action that we can do is to transfer an exponential value in the linear environment to the exponential environment. Notice that when we do that, we erase the value from the linear environment. The third action is to create a copy of a program in the exponential environment and to put the copy in evaluation positions. Notice that now the original program remains in the exponential environment. And the last action that we can do is the applicative action. Here we pick a lambda abstraction in the linear environment and pass to it an input built from an external context C, together with programs and values taken from the linear and exponential environment. Notice that here we erase values coming from the linear environment, but we leave unchanged programs in the exponential environment. Now that we have a tuple-based transition systems, we define equivalence between tuples as trace equivalence. And the reason why we choose trace equivalence rather than, for instance, by similarity, is that by similarity is still a two-fine equivalence. In fact, even if working with tuples, by similarity invalidates distributive of lambda over probabilistic choice. And that is because by similarity is sensitive to branchings. However, if we look at the transition systems of the two programs involved in the distributivity equation, we see that even if they are not dissimilar, they are trace equivalent. And that's not a coincidence. In fact, we can now state the main result we prove in our paper, namely that trace equivalence on the tuple-based transition systems is a congruence and actually coincides with contextual equivalence, meaning that it is fully abstract. Concluding, in our work, we have defined a resource-sensitive trace equivalence for a linear lambda calculus with algebraic effects and explicit copying. Such an equivalence is defined by endowing the calculus with an interactive semantics given as a resource transition system. Our main result is a full abstraction theorem stating that our trace equivalence coincides with contextual equivalence. Concerning future work, what we would like to do is to investigate other notions of resource-sensitive equivalences, such as those akin to bomb tree-like equivalences. Moreover, we would like to extend our trace equivalence to calculi with graded modalities in the spirit of coeffects, as well as to design a quantitative refinement of trace equivalence, so to come up with a notion of a resource-sensitive distance between programs. And last but not least, we would like also to extend our trace equivalence to quantum higher-order calculi. That concludes my talk, which I hope you have enjoyed. Thank you very much for the attention.
Thank you very much for your talk, Francesco. Are there any questions? Please raise your hand or put something in the chat in case you want to make a comment or ask a question here. I see that Nauki has a question. Nauki, can you?
Yeah. So is there any good proof method for your notion of trace equivalence? Any practical useful proof method?
Well, it depends on what you mean with proof method. I mean, on the, let's say, on the method theory side, the proof of full abstraction is a bit complicated. It is elementary in the sense that it just uses elementary techniques, but it has a lot of bureaucracy. And we would like to simplify the proof in that respect. And on the side, let's say on the theory, not on the meta theory, I guess with proof method, you mean something like
I mean, proof method of proving two given program, equivalence of two given programs.
Okay.
Based on
so
your definition of trace equivalence. So you said that by similarity discriminates too much, but advantage of using one of the advantage of using by simulation is, in fact, we can use it as a proof method, right?
Yeah, so we have not developed proof techniques for that, but I think something could be done because we define trace equivalence actually by defining by similarity on a listed transition system. So instead of having monadic transition systems in which you have states which are tuples and then you have these monadic transitions, we lift the system so that states are just monadic tuples, and we define by similarity there, which coincides with trace equivalence in the non-lifted systems. And I guess that there are some up-to techniques that could be defined, but we haven't really looked into that. So I have good feelings, but no formal answer to your question.
Okay, thanks.
Okay, there's a question by Paul Levy who has raised his hand.
Hi, Francesco. I wonder, naive question, is it possible to see this trace semantics as a denotational semantics?
I do not know, actually. I haven't thought about that because so the point, I don't know what happens because we work with tuples of programs, and if we just look at a program in an empty tuples and see and think about it as a denotational semantics as a program, I do not know what happens.
Okay.
So maybe it is possible, but I do not have a precise answer to that.
Okay, thanks.
Okay.
Thank you.
Rafael, do you want to say something? Rafael Romero?
Yeah. Thanks for the talk. It was quite nice. So at the beginning, you mentioned that the calculus used a call by value strategy. So having a strategy by itself, wouldn't that, how does it impact in the equivalence, since, well, having a strategy by itself, shouldn't it be impossible to do this duplication and evaluation, order? Is it necessary to have it there to the order? You couldn't.
No, it is not necessary. The way we choose call by value is that because in call by value you have more of these duplicate and then evaluate, or vice versa phenomena, which you do not have in call by name. And I think in call by names is easier to achieve full abstraction, but I'm not entirely sure about that. So the reason why we choose call by value is that if we want to study the interplay between linearity and effects, in that setting is more challenging than in call by name in general. But I think, I do not see any reason why our techniques should not work in call by name. But in call by name, maybe you may have some, let's say, lighter notions of equivalence, which is still fully abstract. But still, I think that our trace equivalence works straightforwardly in call by name as well.
Yeah, that's what I was thinking. It should be independent of the strategy.
Well, you should just slightly modify the clause, the applicative clauses. In that case, you ask that the context takes some stuff and produce a value. If you're in call by name, you do not need to produce a value. Just an arbitrary terms is fine, and that would be the only difference.
Yes, exactly. Oh, thanks.
Thank you.
Okay. Any other questions? And I have a question, maybe a bit naive question. So I looked at this these evaluation rules. So you create these traces, and the way I understood it, you start from empty with an E, and then you start your trace. And at a certain point in the last action, you have to see this context coming in. So I was wondering, where does that come from? Is it also stored somewhere that's implicit or so? Or did I miss
no,
it?
this is something that the adversarial is providing. So then that clause you play against any possible context that builds a value, essentially using resources that you have in your let's say internal environment.
Okay. So but there is another kind of a stack of context that's kind of changing or so.
Yeah.
Just the environment.
yeah, there is this environment in which one collects the values which are produced during the evaluation. That is the resources you have at your disposal. And then when you have these applicative actions, you also consider an external context. So that comes from a completely external environment.
Okay. Okay. Thank you. Yeah. Thank you. Other further questions or comments?
There is a question in the chat.
There's a question in the chat.
By Kenshi.
Okay, what is assumed about the observation function on programs? Is it an arbitrary function on terms or on their denotation? Okay, there is essentially no constraint on the observation function, but it is defined on the results of evaluation of programs. And then, of course, once you have that, you can extend it to programs using post-composition, but it is defined on the result of evaluating a program. And actually, there are some canonical choices in which, for instance, you say, okay, I just want to observe convergence plus effect, and in that case, the function is a unique function that goes from T of values, where T is the monad, to T of 1, where 1 is the terminal object. That's just sort of canonical choice, but there are also other choices which work fine.
Okay, thank you. Do I see any more questions or comments? No, I don't see anything. Thank you for the explanation. Okay, so thank you very much for the talk, and thanks to all the 4 presenters in this session for the talk. Thank you very much. And we now have a half-an-hour break, coffee break or lunch or dinner or whatever your time schedule predicts you. Thank you very much.